The tech giants sell you the dream of infinite threads and seamless workflows. They tell you that your 2025 flagship processor can handle anything you throw at it simultaneously. They show you glossy advertisements of creative professionals editing 5K video while rendering 3D models and attending a video call. But here's the cold, hard reality that they hide in the fine print of their technical manuals. Your computer is a liar. It is not doing all those things at once. It is a frantic, panicked juggler, tossing one ball into the air just long enough to catch another before it hits the floor. In a single second, your processor might switch contexts over 10,000 times. That means 10,000 moments where your expensive silicon is doing absolutely zero productive work for you. It is merely shuffling papers, moving data from one shelf to another, and trying desperately not to forget what it was doing. This administrative bloat is the tax you pay for the illusion of multitasking. If you find this fascinating, or if you are tired of being lied to by marketing departments, subscribe to the channel now. We are stripping away the plastic casing to see the ugly clockwork beneath. Imagine a world where every time you took a phone call, you instantly forgot your own name, your home address, and what you were doing. To prevent this, you would need to write everything down on a notepad before answering the phone. This is the fundamental problem with interrupting a running process. When a program runs, the CPU lives in the moment, its entire universe contained within a few high-speed registers. These registers are the CPU's short-term memory, holding the volatile results of your current calculations. If the system switches to a new process without a plan, that new process will inherit the old one's baggage, leading to a digital catastrophe. To prevent your spreadsheet from thinking it is a fragment of a video game, the system must perform a context switch. It is a transition where the CPU changes its execution context from one process to another. It sounds elegant in a textbook, but in reality, it is a desperate scramble. The operating system must freeze time, take a snapshot of every register, and bury that data in memory before the new process can take over. This is not a feature of modern computing. It is a necessary evil, a frantic workaround for the fact that our processors are fundamentally incapable of thinking about two things at the same time. A context switch does not happen by magic, and it certainly does not happen for free. The operating system must stop being a facilitator and start being a micromanager. It has to run specific code to capture the state of the departing process and restore the state of the incoming one. The great paradox of computer science is asking how a CPU can save its own state without altering that state in the process. It is like trying to take a photograph of your own camera while you are using it. You cannot use the registers to save the registers because you would overwrite the very data you are trying to protect. This video explores that exact problem by looking at how interrupt-based switching works in systems that are supposedly smart. We like to think of our computers as logical, but they are built on a foundation of constant, violent interruptions. Modern computing is built on the back of the interrupt. Without it, your computer would be a glorified typewriter that freezes every time it waits for a hard drive to spin up. But as we will see, this foundation is cracked, and the fixes are as expensive as they are clever. Interrupts are the whips that keep the CPU moving. A process can be interrupted in two distinct, equally disruptive ways. First, there are software interrupts, which happen when a program realizes it is too weak to do something on its own and begs the operating system for help. Then, there are hardware interrupts, triggered by external devices like timers or network cards that demand immediate attention. When an interrupt occurs, the CPU does not finish its current task. It completes the current instruction and immediately forces the program counter to jump to a piece of code called the interrupt handler. This jump is the first major challenge in the architecture of chaos. The moment the interrupt occurs, the CPU overwrites the program counter. In an instant, the system has lost its place in the book of instructions. It is as if someone slammed your book shut and threw it across the room while you were mid-sentence. To save the process state, the interrupt handler must act fast to capture the register values. The standard procedure is to push these values onto the stack, a region of memory used for temporary storage. However, this introduces a problem that software cannot solve on its own. The stack pointer currently points to the user program stack, but the operating system is a jealous god. It demands its own protected space, the kernel stack, to perform its duties. If the OS tries to use the user's stack, it risks corruption, security breaches, or a total system collapse. This is where we see the limits of pure programming. Trying to solve this with software alone leads to a recursive nightmare of manual register saving and stack switching that is simply too slow for the real world. The program counter is already lost by the time the software even realizes an interrupt has started. This reveals a cold, hard principle of the industry. Sometimes hardware must step in to save the software from itself. This is the point where the silicon designers at companies like Intel and AMD start making choices that affect your wallet. They have to decide how much extra circuitry to add to the chip to make these interruptions less painful. There are two general approaches to this hardware-assisted salvation, and neither of them is perfect. The first approach is the use of multiple register sets. Instead of having just one set of registers that everyone has to share and fight over, the CPU provides several duplicate sets. When an interrupt occurs, the CPU does not bother saving data to slow memory. It simply flips a switch and begins using a different set of registers. This leaves the interrupted process's data untouched and pristine, sitting in a dormant part of the chip. It is a brute force solution that favors speed over elegance. In this design, the processor operates with a common register set for the peasants, the user programs, and a privileged register set for the royalty, the operating system. When the alarm bell of an interrupt rings, the CPU switches to kernel mode and activates those privileged registers. The operating system can then leisurely copy the saved values to memory structures like the process control block, or PCB, before deciding which process gets to run next. It sounds like a dream, but in the world of high-tech manufacturing, dreams are expensive. If this design is so simple and fast, why isn't your $1,000 smartphone using it? The answer is economic greed disguised as engineering efficiency. Duplicating entire register sets is a massive waste of silicon space. Modern processors do not just have a few registers. They have hundreds of them, along with complex execution units and caches. Every square millimeter of a chip costs money. The villains. In this story, the hardware manufacturers realized long ago that it is cheaper for them to make you wait a few microseconds than it is for them to double the amount of expensive circuitry on every chip. Because of this, modern architectures prefer more subtle, automated methods. The second approach is partial hardware automation. Instead of providing a whole new set of registers, the CPU is hardwired to automatically save the most critical information the moment an interrupt hits. Before the software even knows what is happening, the hardware pushes the program counter and the stack pointer onto the operating system's kernel stack. It is a protective reflex, like blinking before an object hits your eye. Once these critical values are shielded from the coming chaos, the operating system software takes over to save the remaining, less vital registers. This hybrid approach is the middle ground that allows companies to sell you reasonably fast chips without blowing their production budgets. They give you just enough hardware to prevent total failure while leaving the heavy lifting to the software engineers. It is a compromise that works, but it still leaves you, the user, stuck with the overhead of a system that is constantly interrupting itself. Some architectures, like the older x86 designs, tried to go even further with fully hardware-based context switching. They created a special structure called the task state segment, or TSS. In this fantasy world, the processor handles almost everything. When an interrupt occurs, the silicon itself copies the entire register state into a specific memory structure. From the software's perspective, the context switch happens almost magically, with no manual labor required from the programmer. It sounds like the ultimate solution, yet major operating systems like Linux and Windows almost never use it. Why would they reject a powerful hardware feature? Because it is a trap. The TSS mechanism is rigid, complex, and ironically slower than a highly optimized software routine. The tech giants realized that by doing it in software, they could cheat. They could choose to save only the registers that are actually being used rather than blindly copying everything. This is the survival strategy of the OS developer. Do not trust the hardware to be smart. Just make the software fast enough to hide the hardware's flaws. Understanding this collaboration, or rather this uneasy truce between hardware and software, reveals how your computer actually functions. It is not a smooth, continuous stream of logic. It is a series of thousands of tiny, violent stops and starts. Context switching is the glue that holds our multitasking world together, but it is a glue made of friction and lost time. The silicon doesn't care about your productivity. It only cares about the next instruction and the next interrupt. We live in an age where we are told that more cores and more threads are the answer to everything. But more threads just mean more context switches. more administrative overhead, more opportunities for the villainous tech companies to sell you a $3,000 solution to a problem they created by making software more bloated and inefficient. They want you to believe that you need a 2025 processor to handle a basic workflow, when the reality is that the system is spending a huge chunk of its power just managing its own interruptions. So how do you survive in this world of digital friction? The lesson is simple. Stop believing the lie of infinite multitasking. Every time you have 50 browser tabs open while a music app, a chat client, and a system update are running in the background, you are forcing your CPU into a state of constant, inefficient context switching. You are paying for the electricity to let your computer juggle, rather than to let it work. To protect your wallet and your sanity, realize that even the fastest processor is most efficient when it is allowed to finish what it started. As we look toward the future of computing in 2026 and beyond, the battle between hardware and software will only intensify. We will see more specialized accelerators that try to offload this work, but the fundamental problem remains. A single CPU core can only ever be in one context at one time. Everything else is an illusion, a magic trick performed with registers and stacks. It is a brilliant trick, but one that comes with a price tag we all eventually pay. In the end, context switching is a testament to human ingenuity and a reminder of our limitations. We have built machines that can perform billions of operations per second, yet we still struggle with the simple act of changing our minds. The next time your computer feels a little slow, or your laptop fan starts to scream, remember the frantic juggling act happening inside. Your machine is fighting a constant war against its own nature just to keep your cursor moving. Take this knowledge and apply it to your digital life. Streamline your processes. Close the apps you aren't using. Don't let the administrative bloat of the digital world bleed into your real-world productivity. The tech companies want you to keep buying more power to compensate for their inefficient designs. Don't give them the satisfaction. Be the master of your machine's context, rather than a victim of it. I hope this deep dive into the guts of your processor has given you a new perspective on the seamless world of modern technology. If you want to keep uncovering the truth behind the marketing fluff, make sure to subscribe and stay tuned for our next investigation. Knowledge is the only way to survive the planned obsolescence and hidden taxes of the tech industry. Subscribe now, and let's keep the silicon honest.